Quotients of polynomial functions. We want to recall that a rational function f of x is given as p of x over q of x, where p of x and q of x are polynomial functions and q of x is not equal to 0. When we divide two polynomial functions, the rational function that is created could have one or more of the following discontinuities. You could have a vertical asymptote. They're vertical lines where the function is undefined. They could have holes, which are points where the function is undefined. You could have horizontal asymptotes, and you could have oblique asymptotes. We will look at all of these discontinuities in more detail in this section. If you have a discontinuous rational function, it will have a denominator which will have zeros, resulting in holes and asymptotes. So let's look at that. Holes will occur in a graph of a function when the indeterminate form 0 over 0 occurs. How do we know where there is a hole in a function? So let's look at an example to understand that. You have the function f of x equals x squared minus 1 divided by x plus 1. So if you take this function and you try to find out if there is any discontinuity, you can rewrite this as x squared minus 1 can be written as x squared minus 1 squared, which is a difference of squares. So it can be factored as x plus 1 times x minus 1 divided by x plus 1. So this is equal to x minus 1. And you know that at the value of x equals negative 1, so when x equals negative 1 for this function f of x, what would we get? We would get 0. So you put negative 1 over here and negative 1 over here, you'll get a scenario where you have 0 over 0. So if the function has a value of 0 over 0 at a value of x, that means at that value of x there is a hole. So therefore, there is a hole, discontinuity, at x equals negative 1. And we've learned this in grade 11 already. And what would we do to graph this function? Well, we will draw the function as f of x equals x minus 1, which is this line here, which has a y-intercept of negative 1. But at the value of x equals negative 1, which is right here, we will indicate that there is a hole in the graph. So right here, there would be a hole in the graph, and so there's a break there. So we would call that a discontinuity. Or a hole at x equals negative 1. Okay, so that's how we would graph it. Let's take another example. Find the holes and vertical asymptotes for the following function. Use the information to sketch the function. So you look here, you can see that you have a rational functions, y equals negative 3x minus 9 divided by x squared plus x minus 6. So the degree of the numerator is less than the degree of the denominator. So by default, you have a scenario where the horizontal asymptote is the y-axis. Okay, we're going to factor the denominator here, and so we're going to get y equals negative 3x minus 9 divided by x plus 3 times x minus 2. We can also factor out the negative 3 in the numerator and write this as negative 3x plus 3 divided by x plus 3 times x minus 2. And these cancel out, and this is simply negative 3 over x minus 2. So how do we graph this? Well, this would look like the graph of a reciprocal function, which has a vertical reflection and has been shifted horizontally to the right by 2 units, right? So you're going to have a vertical asymptote at x equals 2. So what happens though when at the value of -3? Let's see what happens at x equals -3. At x equals -3, this ends up as 0 and this ends up as 0. So you get a scenario of y equals 0 over 0. Therefore, we have a hole at x equals -3. And what happens when x equals +2? What happens when you put x equals +2? Well, you're going to have the function as y equals -3 over 0. So if you have a scenario where you have a constant divided by 0, that means that value of x, you're having a vertical asymptote. So therefore, we have a vertical asymptote at x equals 2. So all of this is giving us information about this graph. It tells us where the holes are, where the vertical asymptotes are. And so we can use this information now to kind of sketch the graph of this function. So I'm going to now I'm going to first draw the vertical asymptote at x equals 2, which will be right here. And write the equation always beside it. So here we have x equals 2 as the equation of the vertical asymptote. We also have a horizontal asymptote for this. There is horizontal asymptote at y equals 0 because the degree of the numerator is less than that of the denominator, and that will be this line here, and I'm going to write its equation next to it, y equals 0. So you're going to have this function typically, in the reciprocal function, parent function 1 over x, you have 1/2 here and the other half on this side. Because of this negative, it's going to be reflected vertically. So you're going to have the graph on this side and this side of the function. If you wanted to kind of get more points to see, graph some points so that you can see what it looks, you could make a table of values. You could take the parent function and map it. So the parent function will be y equals 1 over x, and the transform function is x plus 2 and -3y. So if you have a table of values for the parent function, you can then map it and get the points that you can just graph for this. So let's say for the parent function, if x was -2, y would be -1/2. If x was -1, y is -1, x is 0. It's undefined, of course. If x is -0.5, value of y is -2. If x is 0.5, the value is 2. 1 and 1, 2 and 0.5. So we can take these points and get some points for what would it look like for the function we have here, which is y equals -3 divided by x minus 2, right? So this one, every x value, you add 2 to it. So this becomes 0. This is 1.5. This is 1 and 3. This is 1.5 and 6. This is 2.5 and -6. This is 3 and -3. And this is 4 and -1.5. So when we take those points and we go to our graph, we kind of get some points that gives an idea of where it's going to be. So let's just take some points there. 3 and -3 would be this point here. 4 and -1.4 and -1.5 would be right here. 1 and 3. So that's 1 and this is 1 and 3 on this side. And 0 and 1.5. 1.5 5 and 6. Yeah. So you can see that the function is having approaching, it's like this side. So this is how the graph of the function is. Okay. And we also have to account for the hole that's happening at x equals -3. I'm just going to give different color for that. So this is -3, and you have to indicate that this value, there is a hole at x equals -3. So you can see there's a vertical asymptote at x equals 2 and a hole at x equals -3. After checking for common factors, so that's how you decide whether there are holes, examine the function for the existence of either horizontal or oblique asymptotes. So we have seen horizontal asymptotes. If you have a function y equals p of x over q of x, which is ax plus b divided by cx plus d, and it has no common factors, and you know that, if you want to determine if the function has a horizontal asymptote, we just look at the degree of the numerator and the degree of the denominator. And if the degree of the numerator p of x is less than the degree of the denominator, then the horizontal asymptote will occur at y equals 0, which is the x-axis, always. So these are cases where you will have the horizontal asymptote as y equals 0, because the degree of the numerator here is 0, the degree here is 1, so, and here the degree is 1 and degree here is 2, so again it's the y equals 0, that's the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote for the function will occur as the ratio of the leading coefficients of the numerator and denominator. So I'm just going to write that here as the ratio of the leading coefficients of the numerator and denominator. So if we have an example like this, 3x minus 7 divided by 5x plus 1, where both have degrees of 1 in the numerator and the denominator, then the horizontal asymptote will be at y equals 3 over 5. So it's the ratio of the leading coefficients of the numerator and the denominator. Then you can also have a scenario where you might not have a horizontal asymptote, but an oblique asymptote. To determine if the function has an oblique asymptote, we examine the degree of the numerator, p of x, and the degree of q of x, the denominator. If the degree of the numerator is greater than the degree of the denominator by exactly 1 degree, then the rational function will have an oblique asymptote. So that's the case in which you get an oblique asymptote. So if you look at these two examples, you can see that the degree of the numerator is greater than that, the denominator, by exactly 1. So this is 2, this is 1, this is 3, this is 2. So in both those cases, you will have an oblique asymptote. And the way you would find the oblique asymptote is by doing long division. Okay, so by doing long division, we can find the equation of the oblique asymptote. So let's say we wanted to find the equation of the oblique asymptote for this one here, y equals x squared minus 1 divided by x minus 2. So we will do x squared plus 0x minus 1, because you want to also account for the x term, which is not there. It's 0x, and divide that by x minus 2. So x will be multiplied with x. So you get x squared. X times x is x squared. X times negative 2 is negative 2x. And then you subtract. So this becomes minus, this becomes plus. 0 plus 2x is 2x. Bring down the negative 1. To go from x to 2x, you need a plus 2. So this is plus 2. So 2 times x is 2x, and 2 times negative 2 is negative 4. You subtract, so this becomes positive. 4 minus 1 is 3. This cancels out to 0. So you can see here that in the long division, you got the quotient. This is the quotient. That becomes the equation of the oblique asymptotes. Okay, that is the oblique asymptote. So just to recap, this is called quotient, this is called divisor, right? This 3 is called the remainder, and this, what you're dividing, is called the dividend. Okay, those are terms when you do long division. So in this particular example, the oblique asymptote will have the equation y equals x plus 2. All right? I'm just going to call it OA for short. Let's try the other one too. This one here. What would the equation of the oblique asymptote be for this function? So the function is y equals 3x cubed plus 2x divided by x squared minus 4. So let's try long division. So 3x cubed plus 0x squared plus 2x, and we're going to divide that by x squared minus 4. To go from x squared to 3x cubed, we needed a 3x. So 3x times x squared is 3x cubed. 3 times negative 4 is negative 12x. So even here we're going to write the 0x. So we're going to rewrite this as x squared plus 0x minus 4. Just to account for the term that's not there, we'll write a 0x. So this will be 3x squared, 3x cubed, and over here, when we multiply 3x with 0x, we get 0x squared, so plus 0x squared. And then this will multiply to give us negative 12x. Then we subtract, so this becomes minus, minus, plus, so we end up with 14x as the denominator. So now this is what is the oblique asymptote. So the equation of the oblique asymptote is y equals 3x for this rational function. So let's try an example. Find the oblique asymptote for the given function. Use the asymptotes to sketch the graph. So you have y equals x squared minus 1 divided by x minus 2, where you can see the degree of the numerator is greater than the degree of the denominator by exactly 1 degree. So therefore this will have an oblique asymptote. And let's just factor this expression to see if there are any holes. So y equals x plus 1 times x minus 1 divided by x minus 2. So you notice here that you're going to have a vertical asymptote at x equals 2 because that would make the denominator 0. But there are no holes in this graph, right? So in this case, you're going to have a vertical asymptote at x equals 2. And when you divide, you do long division, you're going to get x squared plus 0x minus 1 divided by x minus 2. You're going to get x times x is x squared minus 2x. Subtract, you get 2x minus 1 plus 2. 2 times x is 2x minus 4. Subtract, you get 3 as the remainder here. And so this becomes the equation of oblique asymptote. So oblique asymptote at y equals x plus 2. So now, what would that look like when we're trying to graph y equals x plus 2? We have two asymptotes here. One is at x equals 2, which will be this line right here. This would be a vertical asymptote. Write its equation beside it. X equals 2. And then you also have an oblique asymptote at y equals x plus 2. So that would be a line with a slope of 1 and a y-intercept of 2. So it's here. Just get some points and we can graph that line. And take our ruler and draw that line, which is y equals x plus 2. So that's our oblique asymptote, and x equals 2 is our vertical asymptote. So those are the two asymptotes in this case, or the two discontinuities in this case. And then we can also find other points. We can find if there is a y-intercept or an x-intercept and graph those points. So there is, if you put x equals 0, put x equals 0 to find the y-intercept, you get y-intercept at x equals 0, and the y-intercept value is, if you put 0 here and 0 here, is 1/2. Okay, and if you want to find the x-intercept, so this is the y-intercept calculations. If you want to find the x-intercept, you put y equals 0 in this function. And if you do that, you get, when you put 0 here, this becomes x squared minus 1 equals 0. And x plus 1 times x minus 1 equals 0. So x could be minus 1 or x could be plus 1. At both of those points, you have the x-intercepts. So the x-intercepts would be at negative 1, 0, and positive 1, 0. And a y-intercept at half, so 0 and 0.5 right here. So you're going to find that this function will have a graph that is going through those points and approaching those asymptotes like that. And you'd also have some points up here. So you could, you need some points when x is, say, 4 and 6 and so on. So if you put x equals 3 and 4 and 5, you can get some points on this side. So let's try that. So at x equals 3, we get the y value as 8. At x equals 4, we put you get the y value as 7.5. At x equals 5, you get a y value of 8. So we can take those points and just to get some points on this side to plot them. So 3 and 8 would be up here. 4 and 7.5 would be here. 6 and 8, or 5 and 8 would be up here. So you can see that this is the function on the other side. You can connect those dotted points and just draw a smooth curve. And there you have plotted the function. Now you have to note that a function may have a horizontal asymptote or an oblique asymptote, but not both. Okay, so you notice in this example you have a vertical asymptote and oblique, but there's no horizontal asymptote. A continuous rational function has a denominator which will never equal to 0. So let's look at this example where we have y equals 2x cubed minus 1 divided by x squared plus 4. So the coefficient here, you can see that the degree of the numerator and denominator are the same. So in that case, you have an oblique asymptote. But you notice here that the denominator is x squared plus 4. So it's going to be a continuous rational function, right? Because this denominator, if you look at this, you will find that if you put x squared plus 4 equal to 0, you get x squared equals minus 4, and x equals the plus or minus square root of negative 4. So you notice here that there are no real roots because you're finding, square root of a negative number. So therefore there's going to be no vertical asymptotes in this case. If you look at the function, you have the same degree in numerator and denominator, so you'll have a horizontal asymptote at y equals 2 over 1, or y equals 2. And then you can also find some points to sketch the graph of this function. Let's say at y-intercept at x equals 0, we get the y-intercept. At x equals 0, we get y-intercept of y equals negative 3 over 4. And then at y equals 0, we can find the x-intercept. So we do 2x squared minus 3 equals 0. 2x squared equals 3. X squared equals 3 divided by 2, which is 1.5. So x equals plus or minus square root of 1.5. We can draw now the sketch of this function using some of the points that we just got. The first one is that there is a horizontal asymptote at y equals 2. So that would be a line that's going like this. Y equals 2. And y-intercept at 0 and negative 0.75. So 0 and negative 0.75. Let's say somewhere here. We have a point here. We have x-intercepts at the square root of 1.5. Let's see, what will those points be? So we have these points. We have 0 and negative 0.75. That's a point we have. Then we have the x-intercepts at 1.2 and 0 and negative 1.2 and 0, because this would be, that's what the x-intercepts work out to. We can also try to find some more points, like at x equals 4. So if you put x equals 4 in this, what x equals 4, what is the y value? Y equals 29 divided by 20, which is 1.45. It also works out that when x equals negative 4, y equals negative 1.4, y equals positive 1.45. So those are some points we can just kind of get to graph this. So this one, and the one we just got, which is 4 and 1.45 and negative 4 and 1.45. So we could just take those points to kind of get an idea of what this looks like. So those x-intercepts, and then 4 and 1.45 and negative 4 and 1.45, and you can see that this is the way this function is. So it has only a horizontal asymptote and no vertical asymptotes, because it has a denominator which will never equal 0. Now here we have our last example. Sketch the graph of the following function using the domain, intercepts, vertical asymptotes, and horizontal / oblique asymptotes. F of x equals x squared minus 4x plus 3 divided by x minus 2. As you can see that the degree of the numerator is greater than the degree of denominator by 1. So there is an oblique asymptote, and to find the oblique asymptote we have to do long division. So let's do that first. So we're going to divide x squared minus 4x plus 3 by x minus 2. So x times x gives us x squared, and x times negative 2 gives us negative 2x. Subtract. So it becomes negative 2x plus 3 here. And to go from x to negative 2x, we need a negative 2. So negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. And we subtract. So we get the remainder as negative 1. And this becomes the equation of our oblique asymptote. So oblique asymptote at y equals x minus 2. So there's an oblique asymptote for this function. Then let's find out if there's any vertical asymptotes. Well, if you see denominator is x minus 2, so therefore there's a vertical asymptote at x equals 2, right? And if you wanted to find the y-intercept, put x equals 0, and we find that the y-intercept is negative 1.5s. So the coordinates are 0 and negative 1.5. We have a point like that. And we can also try to find if there are any x-intercepts. Put y equals 0, right? So 0 equals x squared minus 4x plus 3 divided by x minus 2. So we get x squared minus 4x plus 3 equals to 0. We can factor this as x minus 3 times x minus 1 equals to 0. So x equals 3, or x equals negative 1, sorry, positive 1. So we have 2 points here, 3 comma 0 and 1 comma 0, right? And so that gives us sufficient points to kind of sketch this function. Let's just draw the oblique asymptote y equals x minus 2. So it has a y-intercept of negative 2 and a slope of 1. So that's our oblique asymptote at y equals x minus 2. And let's just put some of the points we got. 0 and negative 1.5. We also have a vertical asymptote. Let's just graph that also at x equals 2. So x equals 2 is our vertical asymptote. Let's graph that also. Write this equation beside it, x equals 2. And then graph our points, plot our points that we have. So we have x-intercepts at 3 comma 0 and 1 comma 0, which is here. And then we have negative 1.5 somewhere here. We have a point. You can get some more points, but you'll naturally find that, because of these asymptotes, you kind of have an idea that your function is going to be approaching them like that. And on this side, it's going to be approaching it like this. So that is the sketch of this function. And now we can try some practice questions.